Hello everyone. Thank you for your interest in our research titled Accelerating Forward-Backward Sweep Power Flow Computation on the GPU. This research is conducted at the California State University, Sacramento by Soumya Shah, who has recently received Master of Science degree from Department of Computer Science, Dr. Maher Zargami, who is an associate professor at the Department of Electrical and Electronic Engineering, and Dr. Pınarmiyan Özçelik, who is an assistant professor at the Department of Computer Science. Let's start by providing key highlights of our study. Electric grids have the essential duty of carrying the electric power from generating stations to the customer, similar to the blood vessels which carry blood from heart towards body cells. And to avoid possible blackouts, the system operators need to keep the power system in steady and stable conditions. In order to do that, system operators utilize tools that perform power flow computation, which allows modeling and analysis of electric power distribution systems. In this study, we focus on forward-backward sweep, or FPS for short, which is a widely used method for performing power flow computation. We accelerate runtime of the FPS utilizing kernels and parallel computation patterns such as segmented scan and reduction running on the GPU. To evaluate our approach, we compare the GPU-accelerated parallel implementation of FPS written in CUDA to serial implementation that runs on the CPU, and our results show that parallel implementation brings up to about 4x total speedup over the serial implementation. Now let's talk about the motivation of our study. Many power flow applications involve compute-intensive, repetitive calculations. Hence, depending on the size and complexity of power systems, performing these repetitive power flow calculations by traditional serial methods may take long hours. Thus, there is a need to reduce the runtime of power flow computation to allow system operators to devise faster remedial actions against disturbances or intermittences by performing hundreds or even thousands of power flow scenarios in shorter amounts of time. And to address this need, several studies have been conducted to accelerate power flow computation using parallel approaches running on multi-core CPUs as well as GPUs. Since FPS has inherent parallelism, it is a good fit to be accelerated on the GPU. However, GPU acceleration of FPS, as we have done in this research, is an understudied area. FPS is used to compute voltage of the nodes and electric currents in the lines of power distribution tree via an iterative computation. Previously, a prior study done by Ablokovich et al. Investigated GPU acceleration of the FPS method by parallelizing the calculation of electric currents and voltages within each layer of the distribution tree. Compared to this related prior work, contributions of our study are as follows. We compute voltages using parallel segmented scan, which allows us to parallelize computation for all layers of distribution tree at once instead of layer by layer fashion as proposed by previous study. Hence, parallel segmented scan approach allows us to fill the GPU with enough work, especially for distribution trees with smaller number of nodes. This in turn allows us to make more efficient use of all the available resources on the GPU by hiding compute and memory latencies. Another contribution of our study is that we compute voltage differences between iterations, which is used to decide whether to end the FPS computation or not, also on the GPU, whereas the previous study ignored this convergence computation and instead performed fixed number of iterations. Hence, our approach allows having only needed amount of iterations, and in addition to computation of electric currents and voltages, it also accelerates the convergence computation. As shown in this above figure, the electric power grid consists of transmission and distribution systems, both of which are composed of wires to carry the electric power. The power is carried towards load centers through a transmission system, while in the vicinity of load centers, electric power is routed towards customers through distribution system. The number of edges or nodes in distribution system are much larger than the number of nodes or edges in the main transmission system, since distribution systems need to carry the power to all retail customers. In terms of topology, a transmission system is in the form of a mesh tree, while distribution systems are configured as tree-shaped radial graphs. In this study, we focus on power flow analysis of distribution systems. Hence, the bottom figure that you see here shows a typical power distribution tree, which has a topology similar to a binary tree. Power flow analysis is utilized to calculate the state of a power system, such as voltages and currents, through mathematical or numerical analysis. Such analysis is necessary for system operators to devise remedial actions ahead of time in case of future disturbances, such as blackouts, which may occur due to imbalance between generated power and overall power demand. We focus on a specific method which is widely used for power flow computation of distribution systems called forward-backward sweep, or FPS for short. FPS calculates voltages and currents via an iterative computation that has two stages known as backward and forward sweeps. The backward sweep stage finds the electrical current of each node by starting from the nodes at the last layer of the distribution tree and ending at the nodes at the first layer. On the other hand, the forward sweep stage calculates the voltages of each node by starting from the nodes at the first layer of the distribution tree and ending at the nodes at the last layer. FPS method keeps iterating, which means it repeats the above mentioned two stages starting from the backward sweep one until convergence is gained. And the convergence is gained when the maximum difference between the voltages of nodes in two subsequent iterations is less than a defined threshold. Now let's talk about how we accelerate the forward sweep stage of the FPS method on the GPU. The forward sweep stage involves computing voltage drops and then voltages of each node. The voltage drop of a node can be calculated independently from other nodes. Hence, this computation can be done in parallel, and we write the CUDA kernel to accelerate this computation. The voltage of a node can be calculated by adding voltage drop values of itself and the collection of its parent and grandparents on the path to the root node plus the voltage of the root node. We use parallel segmented scan to accelerate this step, as will be discussed in the next slide. We can use this example to show how segmented scan can be used to compute node voltages. Assume that the distribution tree only consists of two layers of a binary tree. So here's the first layer and here is the second layer. Voltage values of all nodes should be computed as indicated in this figure. This computation can be converted to segmented scan operation that has the following input and output arrays, where the number of segments would be equal to number of leaf nodes. We have a value array that holds the sequence of values and a flag array that indicate how the sequence is divided into segments. In this example, a flag array holds 1 for each element that begins the segment and 0 for all others. Output array of segmented scan is the same size as the input array. Let's talk a little bit more about the input flag array. We have 4 leaf nodes, 1, 2, 3, 4, and thus we have 4 ones in the flag array, which indicates that we have 4 segments. Parallel segmented scan simultaneously performs separate parallel scans on the segments of the input sequence of values. For instance, to the first segment, which consists of the first 3 input values, a separate scan operation is applied. So here is these first 3 input values, which constitutes the first segment. And if you give this input to the scan operation, your output would be equal to these values, which in turn is equal to voltage of the select node, the first node, and the third node. Although the segmented scan involves some redundant computation, because as you see in this output array, voltages of the first node and the second node are computed twice. A parallel implementation of segmented scan allows us to compute the voltage values of all nodes concurrently, and hence allows us to accelerate the computation. We use inclusive scan by key function of the trust library, which is included in the CUDA toolkit, which allows us to run parallel segmented scan on the GPU to accelerate the computation of voltages. Let's also discuss how we accelerate the backward sweep stage. This stage involves computing injected currents and then currents of each node. The injected current of a node can be calculated independently from other nodes. Hence, this computation can be done in parallel, and we write a CUDA kernel to accelerate this computation. The current of a node can be calculated by adding injected current values of itself and the collection of its children and grandchildren on the path to the leaf nodes. We cannot use the same methodology, which is parallel segmented scan, that we use for computing node voltages in the forward sweep stage to compute node currents in the backward sweep stage. It is because in a tree structure, each node has one single immediate upward node, which makes the node voltage computation a good fit for parallel segmented scan. However, since each node can have multiple immediate downstream nodes, using parallel segmented scan for node current computations is not a viable option. Hence, for now, we compute node currents serially on the CPU. Now let's talk about acceleration of the convergence step on the GPU. The FPS method keeps iterating, which means it repeats the backward and forward stages until the convergence is gained. And this convergence computation involves figuring out whether the maximum difference between voltages of nodes in 2 subsequent iterations is less than a defined threshold. The convergence computation can also be performed in parallel because the voltage difference for each node can be calculated independently from others. And finding the maximum of these differences can also be accelerated using parallel reduction. We use transform and reduce functions of trust library for computing voltage differences and finding maximum difference respectively. Next 2 slides present the results of our study. We implement GPU accelerated parallel version of the FPS method using CUDA, and we also develop a serial version of this method running on the CPU using C++ so that we can compare both versions and evaluate our approach. We collect our results on a system with NVIDIA GeForce GTX 1080 GPU with 8 GB of memory and Intel Xeon E5-1620 CPU with 16 GB of memory. We use 9 different synthetic binary power distribution trees with increasing number of nodes between 1K to 256K. Parallel implementation brings up to about 4x total speed up over the serial implementation. So here is the 4x speed up. And for the parts of the computation that entirely run on the GPU, such as forward sweep and convergence computations, larger speeds up are achieved as the size of the distribution tree increases. As shown here, as the number of nodes in the tree increases, the speed ups of both forward sweep and convergence computations also increase. On the other hand, the speed up of backward sweep does not improve after the tree size of 32K. It is because in our current parallel implementation, a big portion of the backward sweep computation is done serially on the CPU. Application of Amdahl's law to parallel computing indicate that the theoretical speed up would be limited by the percentage of the computation that can be parallelized. And at the tree size of 32K, we start to fully utilize the GPU and hence we start to almost reach the theoretical speedup. Although we achieve increasingly large speedups for the parts of the computation that entirely run on the GPU, for instance, for the forward sweep stage, we achieve up to 138x speedup. Our total speedup does not exhibit the same behavior and instead follows a trajectory that is similar to that of the backward sweep. This can again be explained by the Amdahl's law. Most of the total runtime is spent on the backward sweep computation. Hence, speedup achieved in backward sweep stage dominates the speedup of the total computation. This is the reason why in total computation we do not achieve as high speedup as we do in the computations that entirely run on the GPU. Instead, we achieve total speedup which is closer to but better than the backward sweep speedup. In the future, we plan to investigate acceleration of node current computations also on the GPU using an approach similar to the one proposed by Ablakovich et al., which uses layer by layer parallelization method. When we use this method, we expect the performance of the GPU to be degraded as we move to higher levels of the tree towards the root node. It is because at higher levels, since we have less number of nodes, enough work may not be available to fill the GPU, which would prevent it from hiding compute and memory latencies. However, we still expect the GPU implementation of node current computations to perform better than its CPU counterpart. And this is due to the fact that the GPU implementation of node currents computation would allow us to perform the entire FPS method on the GPU and hence would relieve us from doing data transfers between the CPU and GPU in each iteration. We also plan to investigate the effect of different distribution tree topologies on the performance. We plan to use topologies that lead to less redundant computation in parallel segmented scan, which is utilized to compute voltages in forward sweep stage. We use synthetic binary distribution trees in our experiments, and the binary tree topology introduces fair amount of redundant node voltage computations. So if we have a topology where we have less overlap across different paths from root node to leaf nodes, which means paths or segments share less nodes, we would have less redundant computation. And in turn, our speed up would be improved. The next slide lists our acknowledgements And the final slide lists our contact email and the bibliographic strip of our paper. Thank you for watching our presentation.